I thank the organizers for inviting me to this exciting school, and I hope I won't bore you too much with what I have to say. So I was asked to talk about, well, this stuff, entropy and entanglement, and that's what I'll do. It's a huge subject, and I can only scrape the surface of it, and that's why I call it topics, because I'm not going to cover everything. I mean, you're going to have to study some of this yourself. So first of all, it's important to know something about history, and always, and the notion of entanglement, whoops, let me get this machine here. The notion of entanglement goes to 1935 and was introduced under that name by Erwin Schrödinger, who invented the Schrödinger equation, as you know. And there were two papers. One is in English in the Proceedings of the Cambridge Philosophical Society, and the other is in German in Naturwissenschaften. And the latter paper in the Naturwissenschaften contains the famous cat paradox, which you've all heard about. And both of these papers were written in response to the famous Einstein, Rosen, and Podolsky paper, which started the subject, really. Schrödinger says that entanglement, and now get this, is not one, but the characteristic trait of quantum mechanics. So, in his opinion, quantum mechanics, uncertainty principle, all of that stuff, well, it's important, but the really important thing is entanglement. And of course, at that time, it seemed unreachable. That is, it seemed to be something that was conceivable, but not practical. Well, of course, now it is practical. It's the characteristic trait that enforces its entire line of departure from classical lines of thought. Now, this trait is that two physical systems that are brought into temporary interaction and then completely separated can no longer be described, even after the interaction has utterly ceased, by individual wave functions for each of the two systems. Schrödinger wrote that by their interaction, the two representatives or functions have become entangled. The quantitative theory of entanglement has begun to be developed surprisingly recently. That's one of the things I'm going to talk about, the quantitative theory. And it's been done largely, of course, in the context of quantum information theory and communication and cryptography. Entanglement is now a very big topic, as we all know, at least if you measure it by journal pages and decibels. It is yet to be seen just how important it is. History or future will tell us, but right now there's a lot of noise about it. We shall say something about it in these lectures, and also about von Neumann entropy, the entropy of states, and why these topics are related. So this is this will come in the second and third lecture, the connection between entropy, which everybody knows about, and entanglement, which everybody knows about, and why one measures the other. First, in this very first lecture, I will discuss entropy and its various properties. So this is, if you like, the mathematical part. We have to know just what the key theorems are and use them, learn how to use them. It is important to understand these properties and their proofs. Now, I will not give complete proofs of things, but I'll give partial proofs of some things. But it's important to know what legs one is standing on. And to what extent these theorems about quantum entropy are just a quantum version of classical entropy or not, or whether they're genuinely quantum. Now, a remark. Entanglement arises, this is a historical remark largely, Entanglement arises from the fact that quantum mechanics deals with several degrees of freedom in terms of tensor products of states. So I'm going to review that. Not a sum of spaces. Now this is I know many of you understand this point, but I'm pretty sure that some of you have it mixed up, the difference between products and sums. The sum of spaces, the sum of spaces would be the analog of just a simple Cartesian product, which we don't have. More about this later. Put another way, it is a miracle, in my opinion, that the early founders of quantum mechanics, such as Schrödinger, instinctively headed for the tensor product, which resulted in a linear theory for many body systems, the Schrödinger equation, in fact, instead of having a wave function for each particle, as in Hartree-Fock theory. Hartree-Fock theory is an approximation to the linear theory, as you all know. You make some kind of, well, Hartree first made a product ansatz for the wave functions. Fock anti-symmetrized them to do the Pauli principle and so on. But to me, it's a miracle why they didn't start this way. Because in classical mechanics, each particle has a position and a momentum. So why doesn't, in quantum mechanics, each particle have a wave function? It doesn't. At least that's how I would have done it. But then, of course, you would have a nonlinear theory, which, in fact, you do effectively if you want to do quantum chemistry. But anyway, that's just a side historical remark, but absorb it if you can. Now, I will start with some basic, very basic facts. Now, as I wrote at the top, my apologies to everyone who knows this stuff, but this is supposed to be a summer school. So I'm going to be a little bit pedagogical. I hope you don't mind. Some of you know all of this stuff, and all of you know some of this stuff, but I don't think all of you know all of this stuff. Okay, now in quantum mechanics, each degree of freedom is associated with a separable Hilbert space of finite or infinite dimension. The word separable is there for technical reasons. I'm not going to explain what separable is. Don't worry about it. A degree of freedom can be the state of some subsystem of a larger system, which is the point of view or the application that is most used when people talk about area law for entanglement, things like that. They're thinking about a subspace of some bigger space. But it can also be simply the momenta of particles in a domain. That is, the momenta is one Hilbert space, and the position, so not the position, but something else, spin, for example, can be another space. So the degree of freedom can be lots of different things. Anyway, at each degree of freedom, there's a Hilbert space. It can be the angles of spin or a set of spins, or whatever. The Hilbert space associated to several degrees of freedom is the tensor product indicated by this little O times here, O times, of the spaces. For simplicity here, we take all Hilbert spaces to be finite dimensional. In physics, we do have infinite dimensional Hilbert spaces. Of course we do. But otherwise you couldn't do the Schrödinger equation. But as always, not always, but as usual in this business, people just assume spaces are finite dimensional, so you avoid all kinds of technical nonsense. So I write, for example, H1, 2, ... as many spaces as I want is the tensor product of the spaces H1, tensor product H2, tensor, et cetera, et cetera. Now, I want to be clear about what this means. The vectors in this tensor product are linear combinations, all linear combinations of multiplets of vectors. So a simple vector in this space, a simple tensor product of vectors is just one vector for each space. And then you take sums of such things. So when you take sums of such things, it doesn't mean you add the vectors one at a time. That's not what it means. It's sometimes a little hard to get across, but as you know, in sixth grade, you try to teach students how to add fractions, and they add the numerators, and then they add the denominators. And well, it's a little bit like that. You don't want to do this. So vectors like this, or if you take an orthonormal set for each Hilbert space, and then you take products of them, these form an orthonormal basis for the tensor product. Now, it's important to note this very simple and trivial but important fact, that if I take the tensor product of three spaces, let's say, 1, 2, 3, whatever, that's the same thing as first taking the tensor product of 2 on up, or any number you like, and then taking the tensor product. So it's the same thing as the tensor product of this with the tensor product of all that stuff. Now that's a simple observation. No, not deep, it's trivial. Tensor product is associative, but that will turn out to have lots of implications. Now the observables in quantum mechanics, well, what are they? They're linear, for most purposes, bounded linear operators on this tensor product. Now, not all observables are, but for us they will be. For observable that is not is, say, the momentum, that's not bounded. But we'll talk about bounded. Anyhow, everything is finite dimensional, so everything is bounded. A state on the observables is a positive linear functional, so I'll just call it omega, to call it something, whose value on the identity operator is 1. In the finite dimensional case, these states are given in the following way. The state evaluated on an observable, that is the expectation value of the observable, is the trace of something against A, where A is the guy you're trying to measure. And rho, this guy who's sitting there, is called a density matrix because it's supposed to be a positive semi-definite operator. So it can have zeros, but no negative eigenvalues, self-adjoint with trace equal 1. Called a density matrix. Now again, I want to emphasize positive. Positive means that the state evaluated at anything of the form A star A is always greater than or equal to 0. That's what positive means for any A. Okay, so a state is given, a state is a thing that measures observable. And it's given always in this form because it's a little theorem that's all states. That describes them. There's no other way if it's going to be linear and if it's going to be positive. Okay, so here trace, TR is trace. In case there are infinitely many degrees of freedom, as in the spin system in the thermodynamic limit, for example, then there are infinitely many degrees of freedom. There are infinitely many spins. Or when the Hilbert spaces are themselves infinite dimensional, we have to be a bit more cautious in our definitions. So that's why I'm making everything finite dimensional. But there are little sticky points that come in, but we're not going to talk about that. In fact, we're not even going to worry about it. Okay. Any questions? Yes, sir.
Why did we refrain from identifying states with vectors of rays?
Well, because they're much more general. States are much more general. States identified with a vector are pure states. We'll come to that in the next slide. Those are very special ones. I want you to get a way of thinking of states as vectors. Please. I hope by the end you will. Okay, promise? Yes. All right. So.
But you could say state is a density matrix.
What, beg pardon?
You could say, and you said that the state is a density matrix.
A state is a density matrix. Yeah, that's what I said, yeah. And a density matrix is not given by a vector. Much more complicated.
Wait, and your more abstract definition of state, it was from the space of operators to like real numbers?
Yes, the state of operators are observables, the numbers, and with certain properties. the state evaluated on the identity operator is 1. Okay, we'll all agree to that. And it's positive. Okay, that is, positive operators should give, or positive observables should give positive values when evaluated in a state. Right? That's sort of very basic. But the theorem is that all positive operators are density matrices. But not all density matrices are simple vectors. Okay? Now, here are some great references. If you want to jot this down. Eric Collin has a course which he gave in Arizona, Trace Inequalities in Quantum Entropy, an introductory course. And it's also available on this website. And so this contains everything, more or less everything you want to know. That's Eric there in the yellow shirt. Then there's some very good references on Wikipedia and Scholarpedia. Matrix and operator trace inequalities is one of them. There's another one on strong subadditivity. There are many references. In fact, it seems that the most important success of Wikipedia in mathematics and things like that are things that you can encapsulate simply that really works. I mean, you can look things up and you find things. It's really amazing. Otherwise, you can't find the address of a hotel very easily. But you can find all kinds of theorems very easily. Okay. All right, now. Okay, next thing that you need to build this theory is the partial trace. Now, again, everybody knows this, I'm sure, but let's make sure we all know it. Partial trace. So if I have an observable or a density matrix, but they're both operators, remember that. Let's call it A12 on a tensor product. So this is operator or observable on this tensor product. There is a unique operator, which I'm calling A1, given this guy. A1 is obtained, or written as this partial trace over 2 of A12, the given one. And this is a little bit like when you have a function of 2 variables, you can integrate one of them, and what's left is a function of 1 variable. Well, there's something very similar for operators, and that's called partial trace. And how do you define it? Well, you would like it to have this property, which it does. Namely, if you take any other operator on the first space, anything, think of it as a test, tensor the identity on the second space, and you take its trace with the given guy, then that is the same thing as this guy traced against the given, the arbitrary operator B. There's a unique A1 that does this job, and that's called a partial trace of A12. And you can evaluate it in the following way. If you want to be very explicit about it, you sum over the second indices, put them equal in sum, or more precisely, the expectation value of this A1 in a state V, in a vector V, is given in the following way. You take V tensor orthonormal basis in the second space, take the expectation and sum over the orthonormal basis, and then it's a little theorem that says that this number that you get out this way does not depend on the choice of the orthonormal basis for the second space. Okay. That's a little theorem you have to prove. Okay. Now originally I defined this tensor product for operators, but of course here I'm extending it to vectors, well, the other way around. Anyway, so a tensor product of operators, simple operators, one on the first space, one on the second space. This is a special kind of operator on the product space. Acting on a product vector is the first acting on the first and the second acting on the second. And note that the trace over H12 is given using this definition, very important to notice. It's the trace over H1 of what you get after you do the partial trace over H2, or the other way around. So the trace of A1, which is now defined this way, is the same as if you took the original A1, 2 and traced it out over the full space. So all of that you're supposed to know. Any questions about that? Okay. Now, this is the sort of meat and potatoes of the whole theory of sorry to bore you with this, but it's sort of, it's there. Okay. Next, something you've probably heard about, now it gets a little stickier, is the Schmidt decomposition. A simple example of a bipartite state, that is a state on a tensor product of two Hilbert spaces. Let's call that a bipartite state. This is its density matrix. You know, a simple example is a rank 1 density matrix given by, now we come to the question from before. You take a vector and you just take this thing in the Dirac notation. I think you all know what this means. This is a vector in the space. And the partial trace of this over the second space, for example, you can think of that, well, as, since this is a vector, it's got two indices on it because it's in the product space. So this thing could be considered as a matrix. If you want to think of it, it's got two indices. And I'll utilize that fact. So I choose an orthonormal basis for the two spaces, and I have this vector, this one, which here's the components in this orthonormal basis, very simple. So this psi looks like a matrix, and let me call it R, just to give it a name. Then the matrix rho 2, which I get after taking the trace over the first space, is simply the matrix. Remember, it's got two indices now, because I'm taking the trace over the first space. There were 4 altogether. Now there's 2. Is R dagger R, the matrix product. On the other hand, if I do it the other way around, if I take the trace over 2 first and look at it on the first space, it's the same as R dagger. Now, it's a well-known theorem in linear algebra that the non-zero eigenvalues, there can be zeros, but the non-zero eigenvalues of both rho 1 and rho 2 are identical. The non-zero eigenvalues of R dagger R and R dagger for any matrix are identical. It's a very simple theorem in linear algebra. So let's call them lambda. And as you can see from the structure, it's positive, or non-negative at least. And let these phi 1 and phi 2 be the eigenvectors of rho 1 and rho 2. They're indexed by J. So it turns out, it's very easy to see, that the original vector, this is a vector now, psi, it's not a density matrix, it's a vector, can be written as the tensor product of these two phi's for the same J belonging to the same eigenvalue times the square root of the eigenvalue summed over all J equals 1 up to whatever the dimension is. It's the minimum of the two dimensions if they happen to be different. Remember, I didn't say that H1 and H2 are the same. H1 and H2 could have different dimensions. So this is just a theorem from linear algebra, from looking at the partial trace as a matrix product. The reason for the square root is when I square it, I should get lambda. That's why I put a square root here. So these numbers, which are characteristic of this vector psi, these numbers are called Schmidt numbers. Now I know you've all heard of Schmidt numbers and they're very popular. Well, that's what they are, so you should know that. Okay, now the next topic is really interesting. Really, really, really interesting. This is pure quantum mechanics now. There's no classical, not really any classical analog of this. It's purification. So take a density matrix. Now remember, this could be on one space, two tensor product of two spaces. Anyway, it's a Hilbert space, whatever it is. take a density matrix. It's got eigenvectors. Because it's what? It's a positive, definite, self-adjoint matrix with a finite trace. So. And call the eigenvalues lambda j. And they're, of course, greater or equal to 0 because the density matrix is positive. And the trace is 1, so they sum up to 1. Now, that means the density matrix can be written this way, where these are the eigenvectors and these are the eigenvalues, so there's nothing surprising about that. And we say that rho is pure, again, getting back to this, if there's only one non-zero term. That is, we're back to the case on the previous slide. That's rank 1 density matrix, and it's called a pure state. That a vector is called a pure state in the sense that you make a density matrix this way out of it. And so the norm of this vector is 1. It's okay, so far so good. Now comes the purification lemma. Okay, this is quantum mechanics at its best. For any Hilbert space and any density matrix on this Hilbert space, there's another Hilbert space, in fact, there's lots, and a pure state on the tensor product of the original one that I started with and this one which I claim exists, so that the density matrix that I'm given from the first space is the partial trace over the second space of this pure state density matrix. Okay. Should I repeat that? Everybody got it? Okay. You can always find this, and in fact, you can do it in the following way. This rho 1, 2, which I claim exists, is called a purification of rho 1. And one way to construct it is simply to use this fact up here and think of the index j, which we're summing over, as a vector. As vector components in the second space H2. So that gives you the second space. And think of the sum as a partial trace over that second space. And think of this thing with the vector v with its own indices, and the additional index j, think of that as the vector in H12 that is pure, that gives you a pure state. Here it is. And it just happens to be diagonal in the j basis of H2. That's a mouthful. So if you didn't get it, never mind. All you have to know is every density matrix, however complicated, can always be thought of as a partial trace of a pure state, but in a bigger space. That's what you got to know. Okay? Any question about that? Yes, sir.
You say that there are many purifications.
Yeah.
Can that be quantified?
No, it's infinitely many.
So
Yeah,
is it-
that's all right. I mean, yes. If you want me, okay.
Is there a minimum dimensionality on what the...
Depends on the rank. I mean, you certainly needed the dimension of the number of non-zero eigenvalues. That's okay. That's that. Whoops. Well, yes, but we don't need that. Okay. All right, so this is the purification. Now, there's no real classical analog of this, at least not a useful one that I know about. So we're going to use it for something. And it's really remarkable. As I said, this is pure quantum mechanics. As far as I know, purification was introduced in the paper of Araki and myself called Entropy and Inequalities back in 1970. We didn't call it that. We just used it. So, as we said, whenever rho 1, 2 is pure, the spectrum of rho 1 equals the spectrum of rho 2. We said that whenever you have a pure state on two Hilbert spaces, the spectrum of the partial trace one way is the same as the spectrum the other way. And as I said already, I'm just repeating myself here, that this is the same statement, except in another language, of the well-known theorem of linear algebra, that the spectrum of x stagger x is the spectrum of xx stagger, except for the zeros. Where did the zeros come from? Well, remember, x, the two Hilbert spaces don't have to have the same dimension. It can be completely, they refer to completely different physics. So one could be 5-dimensional, the other 20-dimensional. So doing it this way, you get 5-dimensional. You get a 5-dimensional matrix, and doing it this way, you get a 20-dimensional matrix. So how can they be compatible? Well, they are. The non-zero eigenvalues are the same. But there are a lot of zeros on one side that aren't on the other side. But if we don't care about zeros, the spectrum is the same. Okay, so therefore, if I take any function of a density, one body, one particle, if you like, or 1 degree of freedom density matrix, I take a function of, what do I mean by a function of a matrix? I mean the matrix whose eigenvectors are the same as what I put in there, but whose eigenvalues are f, the function of the eigenvalues of the matrix. That's what I mean by the function of the matrix. And then I take the trace. And since the spectrum, or at least the nuns, I should have said for any f, so that f of 0 is 0. I didn't say it that way. I should have. So the trace of f on the first space is the same as the second because the spectrum is the same. I just finished saying. Okay. Now comes the interesting fact. Suppose I take a function of a density matrix on a tensor product of two spaces. The function I have in mind is the entropy, for example. Entropy is so the sum lambda log minus lambda log lambda. That's going to be the entropy, right? That's the, keep that function in mind. But any function, take any function. And take its trace over the double space, tensor product. And suppose I know, just suppose I have a general theorem about, a fact, not a theorem, a fact about this trace in this function, for example, entropy, that it's less than or equal to what I get if I evaluate the same function, but on row 1. What is row 1? Row 1 is the partial trace over 2 of row 1, 2, remember that. So if I think of entropy, if I say that I happen to know that if I happen to know that the entropy of the whole business is less than the sum of the individual entropy, suppose I know that. Let's suppose for the moment. Then, what can I do? I can purify row 1, 2, as I said, so there's now a pure state on a third 1, 2, 3. I introduce a third Hilbert space. So this density matrix is pure, so that taking the partial trace over 3 gives me row 1, 2. Then the partial trace of f of row 1, 2 is the same as the partial trace over 3 of row 3. Why? Because the spectrum is the same. Why? Because it's a pure state. And likewise, the partial trace over 2 is the same as the partial trace over 1, 3, because I can break this up in any way I like. It's 2 tensor 1, 3, or 3 tensor 1, 2, or whatever. I can break it up in lots of different ways, so I can break it up this way. So this guy becomes the trace over 3 of row 3. Why? Because the spectrum of this and the spectrum of row 3 are identical. That's why. And here this is row 1. I don't change that. Leave it alone. And row 2 is the same as row 1, 3. Why? Because the spectrum is the same. So I conclude from this inequality here, using this little trick, I conclude that the trace over 1, 3, putting 1 on the other side, is bigger than the trace over 3 minus the trace over 1. Originally this was on the other side. Which means, that's what I conclude from this purification, that the trace of f1, 2, f over row 1, 2, I started with this fact, and I end up with this fact, just for free. I haven't done anything. So if it's bigger than the sum, smaller than the sum, it's also bigger than the difference. Came for free. There is no classical analog of this statement. This is pure quantum mechanics. That's why I wrote while we. Okay? Yes, sir.
Wouldn't you say there is no classical analog
All right.
for entropy?
Well, for anything.
For any function?
This just happens, it's true for any F. No, that doesn't have to be entropy, anything. If you have this, if you know this, you conclude that. If you, that's the if, okay. But if you, yes, you have,
So in your bottom equation there, none of those states need to be pure states.
no. So let me start again. I mean, you're almost right, but not.
Just in the final results, you have to have a pure state in one of these.
No.
That's
Okay, let's get that straight. Okay, no, I'm really glad you asked that question, because this is confusing, and if you see it for the first time, it's like this, you don't know. All right, so suppose I have this statement, and I know this for any row 1, 2, I know that this statement is true. Suppose, it's a metaphysical statement at this point, but I'm imagining I know that fact, because there are many facts that I do know. So this happens to be one of them. But suppose I know this fact, then purification, which goes back to the previous slide, says that I can find the third Hilbert space, or in this case, a second one. I called it a second space, but one should now be called 1, 2, and 2 is going to be called 3. So I can find another space, so that the guy I want on the 1, 2 on the first thing. Sorry, it's not 1, 2 anymore. This is 1, 2, and this is row 1, 2, 3. It's the trace over 3. So I repeat, I can find the third space and the density matrix on the third space. I don't have to tell you how I do it. I don't need to know how I do it. Then, so that the spectrum of 1, 2, which is this guy I want, is the same as the spectrum of 3. And so this equals that. I haven't said anything about 1, 2 yet. I have said 1, 2 does not have to be pure. 1, 2 could be anything. 3 I pull out of the cloud. Okay? I'm guaranteed that it's there. And so by jiggling this around, I get this guy. You have to do this little calculation yourself. That this equals the trace of 3. But now you see, I can see what may be bothering you. In the end, I end up with this. But 1, 2, and 3 are just dummy variables. Call 3 2 now. If this is true in general, I can replace 3 by 2. These are just dummy variables like x, y, z. So replacing this by 2, I get f12 which is bigger than the difference. Yeah, lots of questions. Yeah, you had one. Let me.
Well, I think just to clarify the initial condition, it's not that all row 1, 2s within this particular Hilbert space that you're making this statement. You're making this statement for all Hilbert spaces.
Yes.
If I add a 3, I also
Yes,
make it
you're absolutely right. Yeah, absolutely right. But good point, good point. This has to be a general fact for all Hilbert spaces, not just the one I'm looking at. That's a very good point. Thank you very much. You had another question. What? You had.
So would you also require that the Hilbert space 2 can yield a pure state for states 1 and 3?
No, I don't require anything about 2. No, I do not. But remember, 1, 2, 3 is pure. 1, 2 is not pure anymore. 2, 3 is not pure, etc. 3 is not pure. 1, 2, 3 is pure. 3 I get by taking the trace over 1, 2. So it's not pure anymore.
If I exchange 1 and 2 in the
You're
trace
allowed to
1,
do
2,
that.
row 1, 2,
Yeah.
does it?
It's still
is it
true.
different?
Yeah, because these labels, 1,
Yeah.
2, 3, they're just dummy labels, so you can put any label you want on.
No, so I'm saying the third part of the inequality doesn't change. The second part also doesn't change. Does it?
That's right.
Okay, so
I
it's
just-
greater than 0.
Yeah. You got to absorb this. I tell you, this is simple but far-reaching, And if you haven't seen it before, that's why I wrote WOWE. I mean, it's very powerful, it's very strange, and it's quantum mechanical. As a matter of fact, here's the first homework problem. You see, it looks like this new inequality, which I obtained from the old one by purification, might seem to be valid only for special matrices, row 1, 2, row 1, and row 2, that arise after purification. It might seem that the final result that I got, the new inequality, came only through some special sequence of steps which are not reversible. And so maybe there's some hidden caveat in there, but no, there isn't. You're supposed to be able to run this movie backwards. That's the homework problem. So it really is general. Okay. All right. Any more questions? Okay. No. So now I remind you what the von Neumann entropy of the density matrix is. It's the minus the trace over whatever Hilbert space we thought of the density matrix log rho. And remember, the density matrix has trace 1, positive definite. So log rho is negative. Why? Because the eigenvalues are less than 1, because the sum is 1. So every term in here is positive. There are other kinds of entropies floating around. There's the Rényi entropy, for example, which comes with a whole lot of indices, parameters, and various things. But this guy is the one with the most interesting properties. That is, you want all kinds of, there are lots of papers that tell you that if I assume so and so and so and so, which sound very reasonable, then I'm forced to have this entropy. It has nice properties on the products and whatever. Okay. Anyway, that's the one we're going to look at. Here I am just repeating myself. If we have a row 1, 2, the density matrix, we can define row 1, oops, yeah, et cetera, et cetera. Now, the first thing is, which I will prove for you, is subadditivity. S12 is less than or equal to S1 plus S2. Always, no matter what. That's subadditivity of entropy. I don't know who first proved it. I know Araki and I proved it, but I'm sure it was known before. I'm just sorry, I draw a blank on that. Anyway, this is true. Now we use purification, and we end up with S12 is less than the sum, remember? It's less than the sum. That's our starting point. It's a theorem. And by purification, I turn it around and change the indices. So I end up with it's bigger than S1 minus S2. But if it's bigger than S1 minus S2, it's also bigger than S2 minus S1 because I didn't distinguish 1 from 2. So therefore, it's bigger than the absolute value of S1 minus S2 for free. So that's the theorem that Araki and I proved a long time ago, and it's called the triangle inequality. And it has had lots of use in physics ever since. It's used all over the place. Now, this, I remind you, is very quantum mechanical. It's the closest you get in quantum mechanics to the classical monotonicity. What is the classical monotonicity? It's that the S12 is bigger than both S1 and S2. So the entropy of the universe is bigger than the entropy of Professor Brennerby, right? But that's not true because I'm boundless. It's just not true. Quantum mechanically. The universe can be in a pure state, and you and I have plenty of entropy. It's just not true quantum mechanics. The closest you get to it is this rather complicated statement that the entropy of the universe is bigger than the difference in the entropy of its pieces. If you divide the universe into 2 pieces, that's as far as you get. No further. You can't say it's bigger than S1 or bigger than S2. Yes, sir.
So why, like in classical thermodynamics, it's the log of the multiplicity of some system? And so why does this quantity, how is this related?
Well, depending on whether you're doing classical statistical mechanics or quantum statistical mechanics. And anyhow, there is a difference. And remember, the classical entropy can be negative if you do what I think you want to do. But if you, it depends on so many definitions on the market. But what do I want to say? It's true in the thermodynamic limit, and I think that's what you have in mind, certainly, that S12 is bigger than S1. But if we have small systems, it's not true.
How does this measure, disorder in a system?
How does it work?
Well, how does it measure, disorder in a system, this quantity?
Which quantity? S1 minus?
S, just S.
S12?
Just S is trace of rho log rho, as opposed to in classical thermodynamics.
That is, well, look, if you take your classical, take your ordinary Gibbs state, e to the minus beta h, and take the trace. That gives you, the log of that gives you the free energy, right?
Sure.
Right. And then there's an entry, then there's an average energy, right? The difference between the two is called the entropy. If you work out what it is, it's exactly this, where rho, it happens to be e to the minus beta h, divided by the partition function. It's exactly the formula from ordinary statistical mechanics. But I can define it, but knowing that formula, I can apply it to any rho and define it to be the entropy of rho, whether it came from statistical mechanics or not. Okay? All right, so some more ancient facts. Strong subadditivity. S12, if I have three spaces, the entropy is not zero. Necessarily could be, doesn't have to be, just three spaces now. The entropy of 1, 2, 3 plus the entropy of 2, putting that on the other side. There's various ways to write this. 1, 2, 3 minus S23 is less than S12 minus S2. That was proved by myself and Ruskay 41 years ago. And what it says is, one of the ways to interpret it is that if I look at S12 minus S2, which remember does not have to be positive. Remember, it can have either sign. Anyway, in analogy with classical probability theory, let's call that the conditional entropy. Just give it a name. What this says is, when you add a third space, however you add it, the conditional entropy goes down. That's a way to do this. Another way to say it is S of the union plus S of an intersection is less than the sum. Well, let me draw a little picture. It's the only picture I'm going to draw. Here, this is subadditivity. It says the entropy of the whole thing is less than the entropy of A plus the entropy of B. That's subadditivity. That's sort of a mnemonic picture. What does strong subadditivity say? It says if A and B have degrees of freedom in common, so this part is still B, then this part is A, and this part is A intersect B, if you like, and the whole thing is A union B. The strong subadditivity can be thought of as an extension of subadditivity where you allow the two degrees of freedom to overlap. Another way. See, this would be A union B. This would be the intersection. Call that 2. So it's the entropy of the whole thing plus the entropy of the intersection is less than the sum of the entropy. Yes, sir.
Why did you just go to the entropy now? I mean, you're somewhere using the fact that you're purifying.
No purification.
Well,
yet.
but
No, this has nothing to do with...
But then it's then such inequality should be valid for any function, not just the entropy.
Oh, no.
So then why?
Oh, It took years to prove that. It has very much to do with the trace. The function in question is minus x log x. No, this is not a general statement anymore. It's very specific to the entropy.
So the only difference that I see in that function from a general function is that if it's a pure state, that's...
No, for pure state,
it's got
that's
only-
trivial. Yeah.
That's right.
For pure state, it's okay, that's granted. Now, how do we go from there?
Okay.
Yeah, that's, okay. Now, purification says that given rho 1, 2, 3, there's a rho 1, 2, 3, 4 now. That's pure, with partial trace over 4 gives rho 1, 2, 3. So let's play this game again. This becomes S4, and so on, and I end up with this statement. From that, I get that by purification. They look very different. Now, this is very amusing because it says, we know that the entropy of 1, 4, just two degrees of freedom, or 2 subsystems, or whatever. The entropy of 1, 4 does not have to be bigger than the entropy of 4. Monotonicity fails. The entropy of 1, 2 does not have to be bigger than the entropy of 2. It can be the other way around. But taken together, the fact that they have a 1 in common says it's always bigger than the sum, which is kind of amazing. But that's true. We're going to use that later. Now, I want to say a little bit about the proof of this fact. I remind you of the Golden-Thomson inequality, which we're going to use, which says that if I take e to the log a plus log b, so think of this as 2 parts of a Hamiltonian. For example, p squared and potential, for example. And I take the trace, that's the partition function of e to the p squared plus v of x, or whatever. That's less than the partition function I get if I take e to the log a, which is a, times e to the log b, which is b. This thing would be e to the kinetic energy, and this would be e to the potential energy. And it says, and when you work it out, you get the classical partition function, because that's exactly what this becomes. It says the classical partition function, which you learn in the textbooks, is bigger than the quantum partition function, which means the free energy is less. Yes, sir?
Should they be positive semi-definite or strictly positive?
Oh, yeah, they have to be positive, but you can all, this is invariant under multiplication by, if I add a constant to make them positive. Yeah, you're absolutely right. So you're worrying about the fact that v of x might be negative. Yeah, you add a constant to it, it just goes through. Yeah. Okay, so now this, what we really are going to need to prove this is that we need it for 3 factors. That's theorem. If you try to say that this might be less than that, I'm writing this, by the way, as minus log c, but that's just for convenience. To make it plus, it doesn't matter. If I try to say that this is less than the trace of the product, that's wrong. In fact, this doesn't even have to be real. This is wrong. What is right for 3 factors is this thing, which says that if b and c commute, I can put the c plus t on the other side, and I get c plus t squared, and then the integral dt gives me 1 over c. Then this becomes correct if b and c commute. But if they don't commute, this is not only self-adjoint, it's positive. And this is the analog of Golden-Thomson for 3 factors. So this is the key thing. And that was proved in this paper back in '73. Okay, now, yes, sir.
Why is this not true for Rayleigh entropies? You said this is true just for, where does the whole thing fail for? Say, if I take a rho to the n log rho.
Where does it have to be, rho log rho?
Like a Rayleigh entropy, instead of a normal entropy.
I don't know where it fails. The proof is for the ordinary entropy. Just, as far as I know, there's no analog of this. It just isn't. I mean, it's a special to do with entropy. It's a very complicated proof. And it uses the fact that it's the entropy, rho log rho. I don't know what else I can say except that. By the way, there are many papers. There are many papers in which by now there are several proofs of this, more than one, which of course should be the case. Important theorem should have several proofs, and there are. But it's interesting how many papers there are saying that this is now the simplest proof. And the simplest proofs get longer and longer and longer. Today I was looking just for fun. There's a proof, it's advertised as the simplest proof. It's 7 pages long, very dense. It's advertised as the simplest proof. But, all right, anyway, there are lots of ways to look at this, but none of the ways are easy. And it uses the fact that it's x log x. Really? Okay, so essential properties of energy. These are things you should know. Concavity and convexity is what makes thermodynamics work. Nowadays, they don't tell you this in a course on statistical mechanics / thermodynamics. But Maxwell and Gibbs understood it very well. Let's discuss the concavity of entropy. A function, now this is just a reminder for people who are not so familiar. Most of you are, I'm sure. A function f, an ordinary function, is concave if f of lambda x plus 1 minus lambda y is less than lambda f plus 1 minus lambda y for all lambda between 0 and 1. That means if you walk between the point x in some space to the point y in the space, you take a walk and ask what the function does as you walk along this line, it goes like that. That's what it means. It says the value in the middle is less than the mean of what it is at the two ends where you started and finished your walk. Okay. It's convex, that's concave if it's bigger, and convex if it's small. Thus, for example, x to the fourth is convex, and square root of x is concave. Square root of x goes like this, x to the fourth goes like that. Now, x can stand for 2 variables. It doesn't have to be one variable. It can be, for example, energy and volume. And the statement that entropy is a jointly concave function of energy and volume is a much stronger statement than that it is concave in energy for fixed volume and concave in volume for fixed energy. They don't tell you this, but it's key to thermodynamics. If you vary the energy and the volume together, the entropy looks like that as you go between the two endpoints. And that's a stronger statement than saying if you go this way and that way, it's concave each time. It's a much stronger statement. And that is the basis of thermodynamics. Everything in thermodynamics comes from that fact. It is important to understand this very important principle as being at the heart of thermodynamics and the second law. That's it. That's all you need to know. For our purposes, we want to note that the quantum entropy is a concave function of the density. Indeed, if f of x is a concave function of x and positive numbers, then trace of f is f of rho. Like, for example, minus x log x is a concave function of x. Then the entropy, f of rho, is a concave function of density matrices. That's an easy theorem. Homework, prove this. So take a row that's a mean of 2 rows, 2 density matrices, and show that the entropy at the mean, for any mean, you like lambda between 0 and 1, is bigger than the mean of the entropies at the two, row 1 and row 2. Prove this. Okay, that's second homework problem. So, oh, I'm sorry, you asked the question before, and I apologize for that.
Yeah, just you mentioned this subadditivity. I don't understand it intuitively.
what, I mean, we put this.
Well, that's true classically.
Why?
It just
put this
is.
system together and you
It
get-
says anytime you take two systems and you make them interact any way you like, doesn't matter. Let them interact so that the density matrix or the probability is not just the product or sum of the density matrix. Anytime you do that, the entropy goes down. That in the sense that it's smaller than the mean, than the sum of the two.
Is that related to this comparative function?
It's related, but it's not the same. It's related. That's all I'll say, but it's an important fact. And interactions always lower the entropy,
Always
no matter
decreases.
what.
Interaction always decreases.
Entropy. No matter what you do, make it positive or
So in-
attractive, that doesn't, yes, sir. Sorry.
What do you mean when you say overlapping degrees of freedom? What does that mean?
Where did I say that?
When you do that,
Over there?
yeah, overlapping degrees of
That means there are 3 degrees of freedom, which so suppose I have a spin system or whatever, right? And people like to ask, if I look at some region in this space, how is the entropy, what is the entropy of that? Given that the whole thing is, say, in a pure state in the ground state. Okay, well, I could take another region, ask the same question. Then I could take 2 regions that happen to overlap. Right? Why not? And I ask, how does the entropy of the union of these 2 regions compare with the individual? It's the same kind of question, right? Nobody says that the original subadditivity says that the 2 regions have to be disjoint. Then the entropy of the union is smaller than, okay? But now we don't have to say that anymore. Okay.
So if we have time evolution, like the entropy tends to increase.
Yeah,
So the
That's
system,
another
according
story.
to this,
Everybody increases.
Inequality, the system tends to separate into different regions.
no.
I don't quite understand. I mean, what you talk about, if the systems are isolated, they tend to have a higher entropy.
Yeah, the sum of the, that's right.
So as the entropy increases, the system tend to be separated in the future.
No, it depends what you take as the starting point. I have 2 systems which don't even have to be separated. They could be touching each other. They could be on top of each other. For example, I don't know, I could have a spin system and take all the spins on the A sublattice and all the spins on the B sublattice and look at the entropy of the A spins and the B spins. They're right on top of each other practically. And look at the entropy of the whole schmear. It's smaller than the entropy of the A spins plus the entropy of the B spins in any density matrix you like to have. It's important, remember, it's important to know that I'm saying that the entropy of one system is obtained from a density matrix of the whole thing, which I get by tracing out the other guys. It's not, you have to keep that in mind, okay? Then it's true.
To clarify this point, one could say that when you consider observables which are made from the 2 systems, you know more about the system, so the degree of uncertainty will go down and will have a smaller.
Yeah, you could say that. That's a very good point. Okay, you could say it that way too. But I'm a little nervous about this anthropomorphic. But you're right. You're absolutely right. Okay, so where did I? So where are we? Next. Okay, subadditivity. So I'm going to. I have to go a little faster. So, I was told I could go to 12:30. Okay. So I'm going to prove this. So I remind you of Golden-Thompson up here, And I remind you of the Piles-Pogel-Lyubov inequality, which is another very important inequality in statistical mechanics. It says that the trace of e to the a plus b, think of this as two parts of a Hamiltonian, we're calculating a partition function, is bigger than, now it's going the other way this time, it's bigger than the trace of e to the a times e to the expectation value of b in the state A. Okay? That's this. That's the Piles-Pogel-Lyubov. And that's the entropy, the free energy goes down relative to what I get if I just evaluated first order. What this amounts to is first order perturbations here, if you like. You want to think of it that way. Now, let me define mutual information just as the difference of these two. The entropy of 1 plus the entropy of 2 minus the entropy of 1, 2. That's called mutual information. That's the name. Never mind. Now I'm going to prove SSA, this subadditivity for you. And it goes as follows. I said I give very few proofs, but this is a short one, so I can do it. Define delta as S12 minus S1 minus S2, and we want to show that delta is negative. Namely, e to the delta is less than 1. That's what we want to show. And now delta is the trace of rho 1, 2 against what? Minus log rho 1, 2. That's the entropy of rho 1, 2. And now log rho 1 against rho 1, 2. Well, since log rho 1 doesn't depend on 2, I can do the 2 trace, and then I just get rho 1 log rho 1. So that's minus S1. And this one is minus S2. And by part, we use this in Piles-Pogel-Lyubov and fiddle around. E to the delta is less than this thing, e to the log rho 1, 2 minus that. And that is equal to, see, I'm allowed to subtract the rho 1, 2. That's less than the trace of e to the log rho 1 plus log rho 2. But now these guys commute because they're in different spaces. So this is trace of rho 1, rho 2, which is 1, which is what we wanted to prove. That's it. So mutual information is always positive in quantum mechanics. You see, some of the things that are true in classical, in ordinary probability theory go over into quantum mechanics and some don't. And it's interesting, really interesting. I don't understand why, but it's interesting that the really hard theorems in classical probability theory, like strong subadditivity, which is an important theorem in classical probability theory. Strong subadditivity goes through. But simple stuff like monotonicity, that the entropy of the universe is bigger than the entropy of a subsystem, does not go through. I don't know why, but that's it's just like that. So mutual information, which is a rather complicated quantity, is always positive. Okay. Now, strong subadditivity. I can't prove that because that's hard. So again, we try to play the same game. We set delta equals this difference and try to prove that e to the delta is less than 1. That would be this statement up here. And now we follow exactly the same line of reasoning, and we end up with trying to prove that this thing is less than 1. So look at this funny expression. E to the log rho 1, 3 plus log rho 2, 3 minus log rho 3. Now, if I could simply say that that's the same thing or close to what happens if I take the product, namely e to the log rho 1, 3 is rho 1, 3, e to the log rho 2, 3 is rho 2, 3, e to the minus log rho 2, 3. And then take the trace over 2, which will make this rho 3. So I would have rho 1, 3, rho 3, rho 3 inverse. That's 1, and that's rho 1, 3, and that would be 1. If I could do this, I'd be home free. But you can't. Doesn't make sense. Okay. Now, you would like to use this Golden-Thompson again and Piles-Pogel-Lyubov, but you can't. But what you can use is this. And then you can take the traces. You can use that. E to delta is less than that. Now you take the trace over 1, and you get that. And now they commute, and you can do that. You can take the trace over 2. You have rho 3, 1 over rho 3 plus t. That rho 3, and that you can pull that through. 1 over rho 3 plus t squared is 1 over rho 3, and you have this. Okay, so that is all I want to say about that proof. Now, matrix concavity. The triple matrix inequality that I just mentioned is useful in more than one context. For example, it can be used to improve the celebrated Maassen-Oomfink generalized uncertainty principle. I will come back to that, I hope, in the last lecture. This was an important paper in Physical Review Letters, which generated lots of things. And that can be made into a non-trivial quantum generalization. Okay, now for this, the good reference is the Nielsen-Chang book. I think you all know that. It's called quantum, what is it called? Quantum Information Theory, something like that. It's a very nice book, really nice. And I'm going to mention Nielsen again. He has an important theorem. Okay, so what does it say? It looks weird. I mean, really weird. It says you take, now forget about 1, 2, and 3. We take two matrices, A and B, positive, definite, same dimension, everything. And we take an arbitrary matrix K, and this is K dagger. And we make this sandwich, and we take the trace. It's A to the P and B to the 1 minus P. We'll put these powers out. Where P is between 0 and 1. Now, A to a power P is less than 1 is concave in A. And B to a power less than 1, this is less than 1, is also concave in B. So that's easy. But now, the claim is that this object is jointly concave in A and B. That means if I change A and B together, move along the line, this is concave. Now, you say, what in the world does this have to do with physics? Well, not much in this form, but it's what leads to strong subadditivity. So this was the mother of all theorems on strong subadditivity and related facts. We'll discuss some of the related facts. So here, joint concavity means if you change both of them together, it goes like that. The paper, the reference here is the paper I already quoted from 1973. So now what are we going to get out of this? Well, I'm not going to prove this. This is hard. This is really hard. But what we're going to get out of it is the following. Well, the original proof in the Nielsen, in this paper is not the one that Nielsen-Chang gave after 5 years. This was 78 about. But Simon gave another proof, and then there are several more. So now I'm going to use that fact, that seemingly ridiculous fact, which is just mathematics and has no physical content whatsoever, to prove strong subadditivity of entropy. And this route was not the original one that was used by Ruskaya and myself to prove strong subadditivity, but it was discovered by Lindblad. And first thing he does is prove the monotonicity of relative entropy. I have to tell you what relative entropy is. Now, relative entropy is a property of two density matrices. Let's call them rho and sigma. And it somehow measures the difference between rho and sigma. It's a measure of how close they are. And it has all kinds of uses. But we're going to prove that and go from there to strong subadditivity. First, we know that this is positive. That's an example using Golden, Thompson, and Filesfeld and Newmark. This combination, you do the same trick again. this relative entropy is always positive. Now this, remember, is a classical concept, classical probability theory, and its generalization to quantum mechanics is due to Umegaki. Okay, so that's this quantity, and it's positive, okay? Again, this is a rather sophisticated fact. It's one of the things that works in quantum mechanics as well as in classical mechanics. So relative entropy is positive. Now, this relative entropy is jointly convex. And how do you prove that? Well, remember this previous theorem that I just mentioned. Here it is. Whoops. This funny thing, k equal 1. We don't need the k. And take a to the p, b to the 1 minus p. And that's a concave function. That's what that theorem said. So here it is. Take rho to the p and sigma to the 1 minus p. These are the rho and sigma. Will be the a and b mentioned before. And take the derivative at p equal 1. Now at p equal 1, this is rho to the 1, which is 1, and sigma to the 0, which is 1. So this is 1. So I'm allowed to differentiate concavity statement if I know it's really 1 at the end point. So I'm going to differentiate it. If I differentiate it, what I get is this. If I differentiate this at p equal 1, I get a rho log rho from this term, and I get a rho log sigma from that term. So I get the relative entropy, and it's concave, or convex because I've turned things around. There's a minus sign. Now, so what it says is, after you take partial traces, the relative entropy goes down. Again, it's one of these theorems that says if you lose information, the entropy, in this case, goes down. Okay. Well, what is it? Well, all right, the homework is to prove what I just said, but let me not, since I'm running out of time. Okay, so now I take the monotonicity of this thing, I take this fact, and I take alpha beta to be 1 and 2, and I take H alpha to be H1, 2, that's the Hilbert space, H beta to be H3, sorry, I said 1, 2 before, I was wrong, and I make these choices and plug them in here, and I get exactly the statement that I said. That is strong subadditivity of entropy comes from that. And here's the moral of the story, and I guess I have to quit very, very soon, right? Lots of important inequalities. The whole subject of quantum information theory, which is all about what's bigger than what. Lots of important inequalities arise from each other. So it's really only important to get one of them in order to enter the club. That is, there's one central difficult theorem in the subject, that's the strong subadditivity, or if you like, the monotonicity of relative entropy. All of these theorems essentially can be obtained one from another by fairly routine arguments. But there's one nub which is intrinsically quantum mechanical, and if you get one of them, you get all the rest. So the concavity theorem is such an entry point. Here's a useful reference. Now, the next thing I was going to talk about is CPT maps, but I don't have the time, so I'll have to do this afternoon. Okay, thank you for your attention. We have 1 minute. All the questions and answered. 1:30. Okay.